Capacitor selection for a motor hinges on various pieces of data. The motor's frame size, voltage, current, and revolutions per minute are essential, but you also need to note the starting torque requirements, the maximum operating torque requirements, the frequency with which the motor starts and stops, and the ambient temperature of the environment where the motor will operate. Once you've gathered this data, you can calculate the appropriate capacitor size using the formula C equals 2 times pi times F times L divided by volts squared times R, where C is the capacitance in farads, F is the frequency in hertz, L is the inductance in henries, volts is the voltage in volts, and R is the resistance in ohms. For a single-phase motor, you can estimate the inductance using the formula L equals 1.25 times volts divided by 2 times pi times F times amps, where volts is the voltage in volts, F is the frequency in hertz, and amps is the current in amps. After calculating the inductance, you can use the first formula to determine the capacitance. Keep in mind that the calculated capacitor size might require adjustments depending on the motor's actual operating conditions. For instance, if the motor operates in a high torque application, you might need to increase the capacitor size. Firstly, understand the role of the capacitor. In a single-phase motor with a start capacitor, the capacitor provides a phase shift to create a rotating magnetic field, which is necessary to start the motor. The capacitor is typically only in the circuit during startup and is disconnected by a centrifugal switch when the motor reaches a certain speed. Secondly, determine the motor's operating voltage and frequency. The voltage is given as 208 volts and assuming a standard power system. The frequency is 60 Hz. Thirdly, assess the starting torque requirements. Knowing the load that the motor needs to start is crucial. If the load is heavy and requires high starting torque, a larger capacitor might be needed. If the load is light, a smaller capacitor will suffice. Fourthly, check the motor's nameplate or documentation for any capacitor specifications. Some motors have a recommended capacitor value printed on the nameplate. This is usually a good starting point. Fifthly, understand the different types of capacitors. Motor start capacitors are typically electrolytic capacitors designed for intermittent use. They provide a high capacitance value for a short period. Motor run capacitors are designed for continuous use and are typically film capacitors. Since the motor in question uses a single capacitor for starting, it is likely a start capacitor that is disconnected by the centrifugal switch. Sixthly, if there is no existing capacitor to reference, start with a range of values based on similar motors with similar horsepower and voltage ratings. A general rule of thumb is to look for capacitors in the range of 20 to 100 microfarads for motors of this size, but this is a very rough estimate. Seventhly, use the formulas mentioned earlier to estimate the capacitance, but remember these are estimates and the actual optimal value may vary. To reiterate, the inductance can be estimated using L equals 1.25 times volts divided by 2 times pi times F times amps, and then the capacitance using C equals 2 times pi times F times L divided by volts squared times R. However, determining the resistance R is difficult without specific motor parameters. Eighthly, once you have a candidate capacitor, test it with the motor. Connect the capacitor and start the motor. Observe the startup performance. The motor should start quickly and smoothly. If the motor starts slowly or struggles to start, the capacitor value might be too low. If the motor starts very abruptly or makes excessive noise, the capacitor value might be too high. Ninthly, monitor the motor's running performance. After the motor starts and the centrifugal switch disconnects the capacitor, the motor should run smoothly. If the motor vibrates excessively or runs hot, the capacitor value might be incorrect, but there might be other issues with the motor. Tenthly, be cautious when handling capacitors. Capacitors can store a charge even when disconnected from the power source. Discharge the capacitor before handling it to avoid electric shock. You can discharge a capacitor by connecting a resistor across its terminals. 11thly, consider using a capacitor substitution box. A capacitor substitution box allows you to quickly test different capacitor values without having to wire in individual capacitors. This can be helpful in finding the optimal capacitor value for the motor. 12th, consult with a motor repair professional. If you are unsure about selecting the correct capacitor, it is best to consult with a qualified motor repair professional. They can perform tests and measurements to determine the optimal capacitor value for the motor. 13th, pay attention to the voltage rating of the capacitor. The capacitor must have a voltage rating that is equal to or greater than the motor's voltage. In this case, the capacitor should be rated for at least 208 volts. 14th, consider the temperature rating of the capacitor. The capacitor must be able to withstand the ambient temperature where the motor will operate. Choose a capacitor with a temperature rating that is appropriate for the application. 15th, remember that the centrifugal switch plays a critical role. Ensure that the centrifugal switch is functioning correctly. If the switch fails to disconnect the capacitor will overheat and fail. 16th, understand that selecting the correct capacitor is a balancing act. A capacitor that is too small will result in poor starting torque, while a capacitor that is too large can damage the motor. 17th, when testing different capacitor values, start with a value that is slightly lower than the estimated value and gradually increase the value until the motor starts smoothly and runs efficiently. 18th, use a multimeter to check the capacitor's capacitance value. A multimeter with a capacitance function can be used to measure the capacitance of the capacitor. This can help to verify that the capacitor is within its specified tolerance. 19th, listen for unusual noises during motor startup and operation. Unusual noises, such as humming or buzzing, can indicate a problem with the capacitor or the motor. 20th, be aware of the safety precautions when working with electrical equipment. Always disconnect the power before working on the motor or the capacitor. Use insulated tools and wear appropriate personal protective equipment. 21st, consider the motor's duty cycle. If the motor is started and stopped frequently, a capacitor with a higher surge current rating might be needed. 22nd, be aware that the capacitor's capacitance can change over time. The capacitance of electrolytic capacitors tends to decrease over time, which can affect the motor's performance. 23rd, check the power factor of the motor. The power factor is a measure of how efficiently the motor uses electricity. A capacitor can be used to improve the power factor of the motor, which can reduce energy consumption. 24th, consider using a motor analyzer. A motor analyzer is a specialized instrument that can measure various motor parameters, including voltage, current, torque, and speed. This information can be used to optimize the motor's performance and troubleshoot problems. 25th, be familiar with the National Electrical Code or NEC requirements for motor installations. The NEC provides guidelines for the safe installation and operation of motors and capacitors. 26th, if the motor is used in a critical application, consider using a redundant capacitor system. A redundant capacitor system consists of two or more capacitors connected in parallel. If one capacitor fails, the other capacitors will continue to operate, ensuring that the motor continues to run. 27th, be aware that the capacitor can affect the motor's efficiency. An incorrectly sized capacitor can reduce the motor's efficiency and increase energy consumption. 28th, if the motor is connected to variable frequency drive or VFD, the capacitor selection process is different. Consult with the VFD manufacturer for recommendations on capacitor selection. 29th, remember that the capacitor is just one component of the motor system. Other components such as the windings, bearings, and centrifugal switch can also affect the motor's performance. 30th, always follow the manufacturer's instructions when installing and maintaining the motor and the capacitor. Proper installation and maintenance can extend the life of the motor and prevent problems. In summary, selecting the proper capacitor involves a combination of calculations, estimations, testing, and observation. When in doubt, consult with a qualified motor repair professional. The frequency is assumed to be 60 Hz, standard for power systems. The resistance is difficult to determine without motor-specific parameters. Start with a range and capacitor substitution box to quickly test values. This could start with 20 to 100 microfarads and is a rough estimate. Monitor for smooth startup and normal running without vibration and overheating. The capacitor's voltage rating must be equal to or greater than the motor voltage, so at least 208 volts. Consider the temperature rating as well. The centrifugal switch must disconnect the capacitor. Too small capacitance leads to poor torque, while too large capacitance can damage the motor. Use a multimeter to check the capacitor. Listen for humming or buzzing. Always disconnect power. Consult with a motor repair professional if unsure.